Good morning, children. How are you all? I hope you're all fine and healthy, right? See, we have just completed 2 lessons in our physical science. First lesson is matter around us, and the second lesson is motion. And in the second lesson, it is about linear motion of object, and it was also about the 3 different equations of motion and where we to use equations and how we use the equations is also discussed, right? I hope you practice the derivations. The derivations are so very important for examination. The 3 equations of motion, I just remind you: v equal to u plus at, s equal to ut plus half at square, and third one is v square minus u square equal to 2as. Okay, now in the third lesson in our 9th class physical science syllabus, this is laws of motion. When an object is in the motion, Sir Isaac Newton has proposed 3 laws. Okay, depending upon the force acting on the object, depending upon the mass of the object, depending upon the surface on which the object is moving, depending upon some external factors, still some more considerations we take here. Based on all these observations, he gave us 3 laws. Before going to see what are those 3 laws, first of all we should know what is rest and what is motion. For example, when you are riding a bicycle, generally so many of you will come to school riding bicycle. When you look at yourself on the bicycle, you look to be at rest sitting on the seat. Okay, but when someone other than you looking at you, you will be in motion along with the cycle. Same thing you can experience sitting in any vehicle. Okay, whenever we are traveling by any vehicle, make sure that we are all in motion with the speed that is equal to by what speed the vehicle is moving. Okay, that's why we say rest and motion are relative. Relative in the sense not relatives like us. They are comparable quantities. We experience this simple thing. When we travel by any vehicle, we feel that the trees are going back. So with respect to us, trees are in motion, they are going back. Actually, we are going forward. But we feel that they are going back. But you look at your co-passenger, you feel that the passenger is at rest. And the passenger feels that you are at rest. But when any observer outside the vehicle looks at you, to him, both of you are in motion along with the vehicle and you are maintaining the same speed as the vehicle. Okay? With respect to you, you are correct. With respect to the observer outside, he is correct. That's why I said motion and rest are relative. Then how do you define rest in physics? Rest is nothing but whenever there is no change in position with respect to time and surroundings. For example, take a tree. If the time changes, it is there in the same position. With respect to surroundings, the position is unchanged. So the tree is at rest. Like when you look at your co-passenger. After 15 minutes also, he is there in the same position. Motion in the sense, change in the position with respect to time and surroundings. Like the other one, outsider, when he is looking at you, you are in motion. The time is passing by, you are also moving. So there is change in the position with respect to the surroundings. At this second, you are here. Next second, you are somewhere. The surroundings have changed. The time is changed. That is called motion. Okay? Now, Galileo, one of the most historic scientists who is very, very talented, has come up with an experiment telling us that default state of any object is motion, not the rest. Initially, Aristotle thought that rest is the default position. But Galileo conducted some experiments and he proved that rest is not the default position, but motion is the default position of an object. How? He just did some experiment on the inclined plane, turning the angle decreasing and making it into a plane surface. Whenever the angle of inclination is more, the object first slides down due to gravity with high speed, then it tries to move up. But When the inclination is more, the angle is more, like the steep of the steps, it cannot go up to much height. Then in the second case, it decreases that angle. Then it comes down with a lot speed and it moves to a height which is greater than the first case. The difference between the two cases is that the inclined angle, when the ball is needed to go up, that upward movement angle is being decreased. Right? Now coming to the third one, he just made the surface flat. A plane surface. When the ball is sliding down, when it is turning under the plane surface, it just keeps on moving. Now he got it out. Up to what time? Up to what distance? It continues its journey like this. Okay? So, he just went on doing so many experiments according to his hypothesis. He just made a conclusion that on a perfectly smooth surface, the motion is indefinite. In the sense, the ball or an object will be keeping on moving. There will be no rest for the body. The provided condition is that it should be perfectly smooth. Then you may now feel that why it is happening not like that at present. Because practically there is no such a perfectly smooth surface. So that is why the motion is not being forever. It is having an end. Because there is no such perfectly smooth surface that will practically exist. Okay. So if such a surface if you create, then the motion will be indefinite. It will be keeping on moving forever. If motion is not the default position, then how could you imagine the formation of solar system, stars, earth, other planets and all those things? Right? Just think once. Okay. Now, after discussion on rest and motion, now we will be moving towards the laws of motion. The first law of motion, Newton's first law, is called law of inertia. What do you mean by inertia? When an object is in the go, in the sense if it is in the motion, it wishes to continue in motion. It doesn't want to come back to rest. Unless you apply a negative force on it, like applying the brakes, till then it won't come back. Okay, if the object is at rest already, it doesn't want to move. It wants to stay back at rest unless you apply a force on it. For example, a football is in the ground, nobody is kicking. What happens? It will be at rest. If someone kicks it, or else water flows, or wind blows, then only it moves. No. That's what I told. Unless a force is acting on the substance, resting object will be at rest, moving object will be in motion. That inability to change its state, rest into motion or motion into rest, that inability is called inertia. Okay, what Newton said is, as just stated earlier, if a body is at rest, it tries to continue at rest. If it is in motion, it tries to continue in motion unless the body is compelled by an external force. And here we got two types of inertia, static and dynamic. Simply, static is the inertia when the object is at rest, whenever it is straight. And dynamic in the sense motion. Okay, when the object is moving, then that inertia is called dynamic inertia. So the examples, if you take for inertia, like the first activity and second activity, when you place a coin on a thick sheet on a glass, just the glass is covered with a thick cardboard sheet on which a coin is placed. Generally, when you pull it slowly, what happens? Coin falls down, not in the glass, somewhere else, right? It comes along with the cardboard sheet. But here what you do is, just pull that cardboard at once. See what happens. You can try this. It's not harmful, right? Okay, just place some empty glass, close it with a cardboard, keep a coin under. Pull with a single jerk. Make sure that the coin is not vibrated. Then see what happens and write your observation. Another trial, when you play carom board, you arrange all the stack of coins in the middle. You will be hitting that with a striker. Initially all the stack of coins are at rest, so they have static inertia. Just try to hit it smoothly with the striker, they won't move because they have static inertia, they don't wish to move. And how can you make them move? By hitting the coins with a great amount of force with your striker, applying the force from your finger, right? Then they turn into dynamic inertia. That is why you hear the sound. When they hit some place, that force is making it to go back. That is why it is showing some negative force on that. Due to that we will get a sound. That is dynamic inertia. Okay. And very important statement for Newton's first law is that mass is the measure of inertia. For this, you have an activity 3 moving two different blocks of different masses with same force. For example, I'll tell an example, you can read that activity. Lift an empty bag with a finger, your school bag, you can lift, right? Now, try to lift your school bag with full of books. Don't try because it will be very painful, right? I hope you understood the difference. What's the difference? Your finger is same, bag is same. Lifting activity is same. Lift to same height. The difference is that initially when you are lifting an empty bag, it was enough to apply a little amount of force because the bag is empty. The mass is very much less. Now, in the second case, the bag is full of books. So the mass has become more. So the same amount of force is not enough. That is why mass is the measure of inertia. In the second case, the bag is showing more inertia. That's why it's not moving easily. Because the mass is increased. It's all about Newton's first law. Coming to Newton's second law, it's called law of force. Here we get two words. One first thing what you know to know is mass and acceleration are inversely proportional. In the sense, like we discussed in the diffusion of gases, lighter gases diffuse faster because acceleration is inversely proportional to mass. Ammonia had less weight there, so more acceleration. That gas ran faster. Hydrochloric acid was with more weight, so it moved very slow. So for it, let it be for gases, solid, anything, mass and acceleration are inversely proportional. Okay. Now here you will get a word called momentum. Momentum is denoted with a P. It's just the product of mass and velocity of object. Okay. The product of mass and velocity of an object in linear motion is called linear momentum. So simply P is equal to mv. According to Newton's first law, when a force is applied on an object, it is directly proportional to the rate of change of momentum. Rate of change in the sense which is observed per some particular time. So when the time is changing, the momentum is changing. As I told, momentum is a product of mass and velocity. Anyhow, mass is constant, it will never change. So what changes? Velocity changes with respect to time. So change in velocity by time taken is called acceleration. The definition you got in the last lesson, second lesson, right? Change in velocity per time is called acceleration. So as the mass is constant, from delta P, which is the product of mass and velocity, we just move the mass outside because the mass is not changing. We write it as change in velocity by time. Now in the place of change in velocity by time, we write acceleration. So F is proportional to ma. To remove the proportionality, we take a constant called k. When you assume that the k, some quantity is applied as 1 unit, then this becomes F equals to ma. This is the expression for force. Okay, so the statement is that the force applied on the object is directly proportional to the rate of change of momentum. Rate time change with delta symbol and momentum is P. In physics, delta symbol denotes change. In chemistry, delta symbol denotes heat. But don't get confused. Okay, so F equal to ma is the equation of Newton's second law, that is law of force. So this is the expression for force. So here it's all about Rest and motion which are relative. How do we observe rest and motion in the single situation? I mentioned as co-passenger observation and outsider observation. And Galileo proved that on a perfectly smooth surface, the motion of an object is indefinite, but practical world such surface is impossible. Right? So turning that inclined plane into flatter, he just observed the motion. Then we just discussed two laws of motion. First law is law of inertia, and mass is the measure of inertia, and we have two types of inertia, static and dynamic. Static is the inertia at rest, dynamic is the inertia in motion. And in Newton's second law, it's about law of force. Two main points. One is mass and acceleration are inversely proportional, and force is the quantity which is directly proportional to the rate of change of momentum. Finally, we got the equation F equal to ma. Just go through this. You have activities, several activities like first to 6th, if I'm not wrong, up to Newton's second law. Just go through them and just try to write them as activity form. It should not be like a paragraph answer, so that you will get clarity. Right? Okay? So, just follow the video, follow the questions, answer the questions, and in the next video, it will be about Newton's third law and some more derivations and some more discussions. Till then, be at home, stay safe. Thank you.